In this video, we're going to take a look at relative reaction rates from both a conceptual and a calculation perspective. Absolute rates of appearance and disappearance must be measured by experiment. But so long as we have a balanced chemical equation and one of the absolute rates, we can predict the relative reaction rates. That's because these are purely a function of stoichiometry. And a relative reaction rate is how quickly a particular chemical is consumed or produced relative to the other chemicals in that reaction. So how quickly or slowly something disappears with respect to how another component appears or disappears. We're going to be considering the theoretical reaction 2A plus B becoming 3C plus D today. Now the rules in general for these. Reactants disappear. Reactants will always have negative relative rates. Products appear. They always have positive relative rates. And the stoichiometric coefficients from the chemical equation are placed in the rate relation as their inverses. Now, we're going to take that and use these principles to put together the relative rate expression for this particular chemical equation. We've got minus 1 over 2 change of A with time equals minus 1 over 1 change of B with time equals positive 1 over 3 change of C with time equals 1 over 1 change of D with time. Let's see kind of what this would look like in a real reaction. We're now going to carry out a dry experiment with this reaction. Our flask currently contains only A and B. So the A are the red molecules and the B are the purple molecules. We're going to move forward a few steps in time, and at each step we're going to count how many molecules of each chemical are in the flask. So we're at our first time point. We have 8 molecules of A, 4 molecules of B, and no C or D present. All right, stepping forward, 2 of our molecules of A and 1 of our molecules of B were consumed, producing 3 new molecules of C and 1 of D. So now in the flask we have 6 molecules of A, 3 of B, 3 of C, and 1 of D. Let's go forward again. We're going to consume another 2 molecules of A and another 1 molecule of B. We made 3 more molecules of C and 1 more molecule of D. Now we have 4 molecules of A, 2 of B, 6 of C, and 2 of D. Let's do that one more time. 2 more of our A molecules are consumed and 1 of our B. We've produced 3 more C molecules and 1 more D. So now, at this last time point, we have 2 molecules of A, 1 of B, 9 of C, and 3 of D. And all of this is just based on our stoichiometry. Let's graph this. So if we graph that, the red line is for A, the purple is for B, the yellow is for C, and the blue is for D. And we can see that the species that have higher coefficients have steeper slopes in their lines, which is what we would expect. If we take the slopes of each of these lines, A has a slope of minus 2, B minus 1, C 3, and D 1, which fits in with our relative reaction rates. If we compare C to D, this is saying that the rate of D's production is 1/3 the rate of C's production, and that's what we see, that ratio of 1 to 3. Similarly, A disappears at half the rate that D appears at half the rate that A disappears. And that's also what we see. So you can think about this in terms of these fractions. You can also think about it in terms of these stoichiometric coefficients. Let's take a look at how we use these mathematically. This reaction is carried out, and in situ infrared analysis determines that chemical C appears at a rate of 0.0244 molarity per second. What are the relative reaction rates for the other 3 chemicals? We're going to start with A, which I'll go through step by step, and then I'll just put up the calculations for B and D. You can pause the video now if you want to give it a try on your own. Let's begin. we're going to take the terms for A and C out of our set of relative rates and set them equal to each other. So our negative 1/2 change of A over time equals 1/3 change of C with time. We're going to plug in that 0.0244 molarity per second we got in the problem, and now we just need to rearrange and solve for A. We multiply both sides by -2 to get rid of the negative 1/2 in the A term. That gives us -2 over 3 times 0.0244. Do a little crunchity crunch, and we get that the change of A with time is negative 0.0163 molarity per second. And this makes sense to us. A should have a negative rate because it is disappearing, and it should be disappearing at a slower rate than C appears, 2/3 of that rate specifically. We can carry out similar calculations for B. B is disappearing at a rate of negative 0.00813 molarity per second, and D is appearing at a rate of 0.00813 molarity per second. And we can also take a look, another kind of idiot check is B and D should have the same rate, but one should be disappearing while the other is appearing, and that is exactly what we see. So to recap, these relative rates of appearance and disappearance are just capturing the stoichiometry of the equation in a dynamic fashion. In order to figure out all of these rates, we would need to know the absolute rate of one of them by experiment, but once we know one of them, as long as we have that balanced chemical equation, we can predict the rates of all the others. I hope this cleared a few things up. Otherwise, I'll be happy to see you in my office hours.